All right, so now let's talk about defects that occur specifically in ceramics. All right, so we've talked about these vacancies and interstitials. So these can happen also in ceramics, right? So here's kind of a schematic of a very basic ionic ceramic, and we can see that we here have a vacancy, and this particular one is of an anion. So we do have vacancies, we do have interstitials, but we often want to just make it clear that this is anion or cation, for example. So here we have an anion vacancy. We also have a cation vacancy over here, again, missing sites of either cation or anion. And then here you can actually see an example of a cation interstitial atom here. And the one thing to point out here is that vacancies, we expect both of these, both cation and anion. However, on interstitials, interstitials typically only exist on the cation. That's because, as you note here, and what we've talked about before, anions are typically those that are larger. And so we wouldn't expect the larger ion to have an extra one, right, in a spot that's not normally occupied. And so that's why cation interstitials are more common. So again, this is not a hard and fast rule. If you have an example of a system where the anions are relatively small, then that could be the case where you have an anion interstitial as well. But just for the general, we typically only see cation interstitials like you have here. However, the one additional thing that we have to consider when we're dealing with ceramics is charge, right? We always talk about the charge of these cations and anions if we're talking about ionic materials. So we must consider the charge neutrality for these materials when we're looking at defects, because our material cannot be positively or negatively charged. It has to be neutral. And so we can get that by looking at a couple different scenarios of pairing defects together. So we're going to look at a Frenkel defect and we're going to look at a Schottky defect. But the idea is that we have to pair things together so that the charge balances. All right, so let's look at that first one. Let's look at a Frenkel defect. This is a pairing of a cation vacancy paired with a cation interstitial. So you can kind of view it as an interstitial, a cation here moving into an interstitial site, right? So something that normally occupies the cation site goes into an interstitial site. So those two are paired together. So because we've just moved something, the charge balance is still okay, right? It's still net neutral. And again, with this Frenkel, since it is moving something into an interstitial, we wouldn't typically see the anion version of this unless, again, the anion size was smaller than typically observed. So because of that size difference, you're usually talking about cation interstitials. All right, so let's look at an example here, and let's look at the sodium chloride or rock salt structure. So I've got the structure here, right? And so we're talking about the cation, so we're talking about sodium. So that leaves its position. So the sodium was the red. So I basically blocked it out, indicating that there's a vacancy there. And then it goes to the interstitial site, right? Some empty site within this lattice. That's where the cation goes, right? So that's an example in sodium chloride. So we're balancing the charge by having this type of defect occur. And again, normally the cation. The next one that we want to talk about is the Schottky defect. So the way this balances charge in an MX type compound, so 1-to-1, is that we have groups of cation and anion vacancies. So basically we have to have if we have an anion vacancy like we see here, it has to be paired with the equivalent number based on the stoichiometry so that everything is charge neutral. So in this case, it would be 1-to-1. So I have one anion and one cation vacancy. Therefore, since I would eliminate the negative and the positive charge, that would again be neutrally charged. And it's going to fall towards the stoichiometry. So if it's M2x3 you'd have to have two metal, three non-metal vacancies in that arrangement because we need to have charge neutrality. So we have pairs or groups of cation and anion vacancies. So again, let's use the sodium chloride example and look at a Schottky defect in that case. So we're going to have the cation vacancy. So same thing that we saw before. But then we're also going to have one of the anion vacancies as well. So a pair of those two, and you see the charge here, +1, -1. So getting rid of one of these, one of those will balance the charge of the system. So that's important with both of these, is that they're balanced when they occur. All right, so let's look. So that's just, again, removing of both those charges. So let's look at another example just to get a feel for the stoichiometry aspect. So again, with Schottky, it'd have to be balanced. So this one is the perovskite that we talked about very briefly. But perovskite is barium titanate. So we have BaTiO3, right? So in this case, if we tried to remove one of each, a barium, titanium, and oxygen, that wouldn't balance the charge because we would have effectively, as you can see from down here, we would be removing +6 and removing -2, right? So that the balance of charge doesn't matter there. So we have to do it in accordance with the stoichiometry. So if we remove one titanium, as you can see up here, we also have to remove one barium, as you can see here. But then you also have to remove, since this is a -6 charge, that means you also have to remove 3 oxygens for every 1 barium and 1 titanium that you remove, because that's the only way to balance the charge. So you have to basically remove a whole formula unit, 1 barium, 1 titanium, 3 oxygens, for that to be balanced.